Okay, so this is example 8.2 in the textbook, and it's on page 432. And this is an example of trying to find the optimum price, but you have four different classes of consumers. And what the problem is explaining in numbers, I will explain in words. Um, Customer one. Now, when we say customer one, we're not talking about an individual person. We're talking about a class of customers. And this class of customers has a utility of $1.24 per pack for the first pack of these candies. And you will notice that as you increase the number of packages that they purchase, the utility decreases, which is a very common situation in economics. If the very first the very first unit of something I have, I value the most, and then as I have more, I value them less and less, which is why when the first kid has a nosebleed, you take him to the hospital, and when the third kid has a nosebleed, you say, just don't get it on the carpet, right? So anyway, so in all of these cases, you can see that utility decreases with the number of packs that the customers have. So for example, we can say that the total value for each customer for the first pack is going to be what you see here. So I will just copy those across. And then the total utility, not the individual, because the first one you want to think is marginal, right? But the total utility for the second pack is going to be equal to the first pack plus the marginal utility. So I can copy that across. Right? And just to make sure I'm doing this correctly, I'll look at customer 4, and I got 273 down here, and sure enough, I got 273 there. So if I can now then just copy that formula all the way down, you can see that I have these marginal utilities. So here's what we're trying to do. We're trying to say, okay, so depending on the price that I charge per package, each customer is going to have a sweet spot. They're going to want to purchase a certain number of packages because they have a certain utility. For example, if I charge, let's just say I charge $1 per pack, okay? Well, customer number 1 has a total utility of $1.24. So that customer has an excess utility, if you will, of 24 cents for that one pack, okay? As I continue to come down here, all right, so 3 packs would be $3. Now I'm down to 16 cents. 4 packs would be $4, right? Well, now his marginal or her, excuse me, total utility is only $3.96. So at that point, they would not buy that 4th pack. It would not be worth it to them because the additional utility is less than the purchase price. Although here you see, even though that marginal utility was less than the purchase price, we more than made up for it with the earlier purchases. So I can figure out what kind of a basket of goods this customer is willing to purchase just by looking at the total utility and selecting a price to see how that price affects their total utility. Do you follow that so far? Okay. Now, let's pause at this moment and just think in terms of these utility functions. These utility functions are different for each customer. Customer number 2 would not even buy the first pack because the utility is less than $1. Customer 3 would purchase a package, and I don't know, I think customer 4 would also purchase a package. Yes, they would. In fact, customer 4 looks like they get the most utility out of that first pack. All right. So because there are different utility functions for each group of customers, each group of consumers, we have an objective function that is going to be what? Smooth or discontinuous? It's going to be discontinuous, yeah. There's going to be, so this would be a really good type of a example to use genetic algorithms. All right, so now I've described to you how the customers look at their overall purchase of these candies, right? And I just threw a value in here of $1. So let's just go ahead and put $1 there. All right. And so now what I can do is I can say, all right, let's just figure out what the total cost is based on the selling price. So it's going to be equal to the number of packs times the unit price, which is going to be an anchored value. So essentially, I can see whether I did this correctly by just copying it down. And sure enough, 10 packages cost $10. All right. Now, for each group of customers, I can figure out where that sweet spot is, how many packages they would want to buy. So how would I do that? Well, all I have to do basically is say, okay, and notice that this row is lined up, which makes it really easy. I could do this one of two ways. I could just very easily go make this equal to the first utility minus the first cost, right? Or if my cost table was somewhere else, what else could I use? What if my cost table was in a different part of the spreadsheet? What function would I want to use? Well, I ought to be able to just use a VLOOKUP, right? Because I've got the number of packs here. So I should be able to just use a VLOOKUP1, find the cost, that kind of thing. Yeah. I could do that as well, yes. I could certainly do that. So you're talking about in this function, I could say equals to this times my unit price, make that my cost function, and then maybe subtract out minus, and now I would go VLOOKUP here, and then I would go to this bigger table, right? And I'd make that an absolute comma, 2, comma. And they're actually in numerical numbers, so I don't have to do anything else. And boom. Well, I should have done clearly I've got this backwards. I should have the VLOOKUP first minus the cost. But I could do that way too, yeah. But for the purposes of this problem, it's going to be a lot easier for us just to go and look up the cost, which is going to be anchored in the column. I'll do it this way. It's going to be look up the utility. I did that wrong again. It's going to be the utility minus the cost, which is going to be anchored in the column, right? So there's 24 cents, minus 8 cents, 27 cents, and 49 cents. So that looks correct in terms of the utility that each group of customers would get from this purchase. Okay? Now, you'll see why I chose $1 as the starting value next, because what I want to do is I want to just double check and make sure that all of these calculations are indeed correct. So 27 cents would be 2, that's correct. 16 cents would be 3, minus 4 cents would be 4, et cetera, et cetera. So all of these calculations for customer 1 look correct to my eye. Do you see anything that is not correct here? Okay. So that also tells me then that I should be able to copy this across as I did before. But let's just be careful here. Let's look at this value. Customer 4 buys 5 packs. So they spend $5, and their utility for 5 packs is $5.61. So that's also correct. Right? Okay. All right. Well, golly, we should just about be done, right? I mean, all we got to do now is just look at this table and figure out where each customer ends up. But no, that's not right. We can't do that. We're not even, we haven't done any real calculations yet, have we? I mean, yeah, we've figured out the total utility of a certain number of packs, but really we haven't even got down to the problems yet. Okay, what we're looking for is what is the maximum number of packages each one of these customers will buy at a given price. What we're trying to do is we're trying to figure out what price to charge the market. All right, but the market is very diverse. And if we pick $1, then clearly there are some customer segments, like customer segment 2, that will never buy our product if we pick $1. So in order to figure out the price that will sell the maximum number of units, we're going to have to figure out what each customer's sweet spot is at that price. So the way we're going to do that, first of all, is we're going to say, okay, we're going to put into max, and we're just going to look at that range of values. Well, with that range of values, the max turned out to be 27. For customer number 2, now remember customer number 2, all those values are negative. So the maximum is going to be the least negative number, right? So I would expect that to be minus 8 cents. And in fact it is. Customer 3 looks like 38 cents is the max. And it is. And then customer 4, we'll see what it says here, is 83. Okay. All right. So at a price of $1, these are what our customer segments look like. 1, 3, and 4 would obviously purchase some of our product. Customer 2 would not purchase any of our product. How many units of our product would each one of those customers purchase? Well, the answer is I need to go back and I need to look up where the maximum occurred, right? So now, this is where I need to do the index and match functions, right? So I can start off by doing this. I can do a match, and the value that I want to look up is that value. And the lookup array is this array, right? And the match type is exact, okay? Now, then I want to do the index, and I want to index this array, and I want the row number to match the value that I just looked up. And I better make this absolute because I want to use it across the formula. Okay. So I'm looking up in the number of packs array to find the value that corresponds to the maximum utility for that particular customer. You see how that works? It should be relatively familiar to you from other work that we've done, index and match, right? What questions do you have? Yeah, good question. So we should probably make an allowance for that in this uh, calculation that says if the max value is less than zero, then we should say zero, because otherwise it's going to look like the customer is going to buy one when in fact they're not going to buy any, right? So we should go back and we should include an if in here. If this value is less than or equal to zero, then zero. Otherwise, look up the value. So we still get a 2 for the first customer, but now when we drag it across, sure enough, we get a 0 for customer 2, which is the answer that we expected to get. We get 2 for customer 3. So customer 3, yeah, the maximum utility is at 38. And customer 4 says the maximum utility is at 3. And sure enough, that's where the 83 popped up, was at 3. So now we've identified the maximum utility for the customer. Just out of curiosity, just because we've got positive utilities here, keep in mind this is the total utility, or the total surplus, I should say, not the total utility, the total surplus. So most customers are going to be surplus maximizing, cost minimize, surplus maximize. So they're never going to go beyond, even though there's still a positive surplus, they're never going to go beyond the maximum because it means it's not as pleasurable. All right. Okay. Now, what else do we need to keep in mind here? Well, we've got a market size constraint as well, right? And so uh, what we're probably going to have to do is we're going to have to figure out some way to work that market size into our calculation. Well, we're only going up to 10 packages, right? So customer 1 and customer 4 really aren't going to affect us because that market is clearly big enough that they're going to purchase all that we're looking at in this model. But how would we constrain the number purchased here? Ought to be pretty simple, right? If I don't want to go above my market size, all I have to do now is just put in a max, right? Or excuse me, min of either this value or the number purchased. And so now let's just test this out. Let's just try a really simple example. What if we reduce this value to 10 cents? Do you think customers will want to buy a lot if we reduce it to 10 cents? Probably will, right? All right, so customer 2, customer 2 had a maximum surplus of 413, right? So theoretically, they would have bought 10 packages, right? But notice we only sold them 5 because the market size was only 5. So we have now constrained the number purchased to be equal to the market size. Right? Does that make sense? No, it doesn't make sense? What doesn't make sense? Well, okay, so it may not be clear because I didn't highlight it. The market size is uh, one of the parameters that has been given to us. I'll make that a little bit darker. All right, the market size is a parameter that has been given to us. So what that tells me is that the research that's been done, well, I'm never going to go below my unit cost anyway. I'm never going to go below 40 cents. So take that as a given, all right? But what this is saying is the utilities that I have are estimated utilities. But the market size is given to me as being 5,000 units for this customer segment. So no matter what I think the utility is going to be, this customer segment's never going to buy more than 5,000 units. So I have to set a boundary on how many packs I, I think I can sell them. I can't sell them more than the maximum demand for that market size. Well, when I dropped the price to 10 cents, which was an artificially low price, customer segment 2 wanted to buy 10 packs. Okay? Now, I'm not going to sell it to them at 10 cents, but I wanted to make sure that I didn't try to sell them more than they would actually buy, which in this case is 5. Does that logic make sense? Okay. All right. So the total purchased then is just going to be equal to the sum of the numbers purchased by each one of the customers, each one of the customer segments. And then the profit is just going to be equal to the number purchased times the margin, which is going to be the price minus the cost. And clearly, since I'm selling below cost, not surprisingly, I'm losing money. This just reinforces the old adage that when you sell below cost, you cannot make it up on volume. Just in case you had any question about that. All right. Well, let me just throw in another number just to see what happens. What if I threw in a number of 40 cents? Theoretically, at 40 cents, I would make 0 profit, right? So correct. At 30 cents, or at 40 cents, I make 0 profit. But you can see the markets now have come below the maximum, right? Segment 1 is down to 9, segment 4 is down to 9, and only segments 2 and 3 are at their maximums. So, this problem looks simple enough. I could probably at this point solve it using a data table almost, couldn't I? But let's go ahead and use a genetic algorithm to solve it. All right, so I'll go into Data, Solver, and start filling out my parameters. Well, my first parameter is my objective function. My objective function is in fact profit, the one that you see highlighted, and I do want to maximize profit. I want to do it by changing my price. And one of the things I said was it really works best if I set some parameters. So, or set some constraints rather on my objective function. So I'm going to add one constraint. Well, the first one I'm going to do is price. I'm going to say the price has to be greater than or equal to the cost. That seems like a no-brainer to me, okay? Why would I look at any prices that are going to create a loss? So it has to be greater than or equal to the cost. What about the upper limit? Well, I don't know really what an upper limit should be. And, we could discuss this for a long time and probably still have to agree to disagree on what the upper limit is. But I am going to make a rash generalization for this problem. I'm going to say that I want to sell to all the customer segments. I know that at a price of $1, I did not sell to customer segment 2. So I'm going to set an upper limit of $1 because I know customer segment 2 won't buy any at $1. Therefore, if I'm above my cost and below $1, that's probably where I'm going to find the best solution to this problem. Does that make sense to you why I would do that? Okay. I'm going to use the GRG nonlinear solver. Not GRG. I'm going to use the evolutionary solver, which is what solver refers to as the genetic algorithm. And what I'm going to do also, because I picked up this nice little hint from doing some research, these are the parameters that the genetic algorithm is using to solve this problem. Now, when I click on solve, you will notice down here at the lower left-hand corner of the screen some rapidly flashing numbers. And those numbers will continue to increase until they reach kind of a steady state. That's going to be the profit. That's the current best profit given the feasible solution that the genetic algorithm has found. What I want them to do is start with a population size of 100 feasible solutions. Well, I've bounded my decision variable to really create fractional values now, right? Because I got one decision variable, which is price. But if I want a population of 100, then I'm going to have to work on that. So, but my mutation rate I'm going to set at 0.5, which is a very high level of mutation. But by doing that, I should converge on the solution fairly quickly. All right, that's the hint that I've been given from other people. So I'm ready to go. I'm going to click on solve, and I'm going to see what I get. And you can see down at the bottom, see how it's flashing? And right now the incumbent is 5,900 99, and it's going through a number of different solutions. Ah, it went over to 6 now. In case you're wondering, yes, these solutions do take a while. Oh, cannot improve on the solution. So what the evolutionary solver came up with was a unit price of 80 cents and a profit of $6 million. And that was the best solution that it could find. Now, did anybody else get a different answer? You're still running? Okay. I'll let you run for a little while and see if you get a better answer. It's the same. You got the 6,000 also? Okay. So it looks like 80 cents is the right price. Now, here's an interesting observation. That's not exactly 80 cents. You see what the value is? 79.998 cents. Okay? Watch what happens if I actually make that 80 cents. Just watch. What happened to the solution? It got worse, didn't it? It got worse by a lot. I mean, it went from 6 million down to 5,600,000, going from 79.998 to 80 cents. What does that tell you about the decision variable, the value of the decision variable? Oh, I shouldn't say that. What does it tell you about the objective function? That's what I meant to say. What does it tell you about the objective function? Extremely sensitive. Okay, yeah, that's fine. Yeah, one of those discontinuities. It kind of fell off the cliff when it got to 80, didn't it? In fact, if I go back, let's run the genetic algorithm again and see if I can get it back down to 79, or whether it's going to force me to stay where I'm at. All right, see, it's already gone up to 59.98. So it already picked up $398,000 in the solution. 59.99 or 5.99, 6. It's back to 6 now. And I'm guessing it's going to find that that's the optimal again. It's not going to go any farther. We'll know in just a few seconds here when it reaches its convergence limit. Yep, there's the convergence. Keep solver solution, which we will do. Okay, and the value again. Well, this time it turned out to be 79.997. All right, so just a little bit different. But again, it's at that far end of the curve where it's discontinuous, to where it actually backed away from it a little bit. It still found the same solution. Right. So it must be the top of the curve there, yeah. Well, okay, so you're raising a really good question. You know, where do you draw the line? Most of the time in, in, in interpreting LP results, you run into the real world test. Um, for example, at 80 cents, I have a margin of 40 cents per pack. At 79, I have a margin of 39 cents per pack. Is that 1 cent per pack difference really significant to me? Most of the time, I would say no. Uh, the example that I'm used to thinking about is feedstocks. When I run crude oil through a refinery, I get a certain margin on that crude oil. If my LP says that that margin for that crude oil differs from another crude oil by less than 25 cents, how significant is that? Well, I can't measure 25 cents. So I would call within 25 cents the same value, crude, right? So you end up with those kinds of challenges. You have to look at this. You say, okay, so is it 89? Is it 80 cents or 79 cents? 79, 79 and a half cents. Maybe what you do is you offer, you know, 3 packs for 79 and, or 3 packs for 80 and get a fourth pack for 75 or something like that. So, okay. What other questions do you have? Yes. Well, simplex would never work because this is not a linear problem. No. Well, neither simplex nor the GRG would find a solution because of the discontinuities from that. So it wouldn't work. Could you use a genetic algorithm on a linear or a smooth nonlinear function? You could. I don't know why you would want to, because the solution methodology, if you'll notice, takes a fair amount of time to come to a solution. And while these problems are fairly small, if you had a larger problem, then the GA methodology would slow down the solution, which would be important if you were trying to do any kind of parametric analysis. You know, here's my base solution now. What if I do this? What if I do that? Well, every time you add another run to the solver, it's going to extend the time it takes to solve the problem. Okay. What else? Yes, yes. The cost is to the customer, is what that you're talking about. The column that is right here. This is the cost to the customer. Yeah. All right. So the actual question you're asking is, can I improve on this solution? And the answer is, I don't know. I don't think I can, but I don't know. And would it be worth it to me to let it run for a lot longer to see if I could get a better solution? In this case, I don't think so because I can I can look at boundary conditions here. I already know if I go to 0.79, it's worse, and if I go to 0.81, it's worse. So those boundary conditions have already got me to a point where, I can go back and maybe I can do that. Maybe if you want, what we can do is we can say, okay, so let's try it. Let's try solver, and this time let's change our constraints. Let's change our first constraint so that instead of 1, we make it 0.81 because we know that's worse. And on the other one, instead of making it greater than our cost, make it greater than 0.79. Okay, so now I've chosen the upper and lower limits to be ones that I know are worse than the solution at 79.99 some value, right? So what if I try to solve it now? Will I get a better solution? My hunch is the answer is no. Well, it's really working hard. You think you could do those calculations that fast? All right. Did not find a better solution. And I suspect it's going to be, again, 79.99 something. 79.9999998. So I've moved as far as I can along the curve without getting to 80 cents. Okay, any other questions? Yes, right. What I would do instead is I would look and I would say, okay, assume I'm the manufacturer. This is the suggested manufacturer's retail price, right? So I'm going to sell whomever the uh, retailer is, I'm going to sell them large volumes, 100,000, 200,000, 300,000 at a time. And when I multiply, say, 100,000 by 0.79999, I'm going to get $79,999. Well, no, there is not a better solution if I don't sell to all the customers because I've got the individual customer utilities were given to me at the beginning of the problem. So I know for a fact that each customer gets some utility out of this this product. So I would not want to eliminate any customer segment as long as they get some utility from it. Well, okay, that is the marginal utilities, right? Okay, so you're saying, for example, that, yeah, okay. let us